Good afternoon. I hope you have a nice evening. Origin will present in this short video the request topic, how to implement the dividend risk model to rate an insurance portfolio. I hope that you at the end of this video you can solve all the doubts you have about this topic. Now, our team consists of Humberto, Aldo, Luis Alfredo, and myself, Diana Gonzalez. For this exercise, it's important to make into account the following data. We have 60 policies of the ordinary life insurance of people at age 40, calculate with an interest rate of 3% and sum insured of 1,000 pesos. Some key concepts are the following. Life insurance, what it means, a life insurance is a contract that pays a death benefits to the policy owner when the insurance die. Premium, what is an insurance premium is amount of money an individual of business pays for an insurance policy. This premium is income for the insurance company. RIN, loss of load. Monte Carlo simulations that are used to model the probability of different outcomes in a process that cannot be predicted due to the intervention of random variables. What we're mainly looking for is to make the value of the variable key as small as possible. What does this mean? Well, we want the loss value to be less than 5% and each policy will be calculated as follows, where it's a life insurance of a person of age X given life coverage for the next omega minus X years will be given at the end of the person's death and the root of the variance multiplied by the variable key as added.
In this project, our main purpose or objective is to create simulations of losses to replicate a real-life insurance portfolio for 60 people, using two different approaches and starting by computing losses for a 40-year-old person. Now, our hypothesis is that we believe our k variable, also known as time sigma, as it is a key component on the calculus of the premium, is going to help converge both probabilities that result in the approach of the Central Limit Theorem and the Monte Carlo simulation technique.
We have an age column X and column B, which has the probability that a person of age X will die in the next year. In this case, the problem asks us to focus on age 40. In column C, we write to the numbers of years that pass from a person of age 40 to the age of 99. This is the probability that a person of age k plus 40 will live that year. Knowing the person of 40 is already 40, then we say that the probability is 1. Now, k dash q of 40 means that a person of 40 survives k years and dies the following year. Therefore, we need him to survive 2k years and die in the next year. And so we multiply these two columns. Then we find the discount value, um, which is p and k plus 1. So we are left with the 1 divided by 1 plus discount rate raised to the k plus 1. And assume you are paid at the end of the year of that, then k is worth 0 in the first of the year. The actual present value of the insurance can be derived in different ways. The easier to do from my point of view is to do the sum product of these columns. Basically, it's to apply a discount factor to each of the scenarios that the person may have. With this, we have the expectation of this insurance, which is the amount that the indically in the cell. There is another way, known as recursive, where we take the probability that a person um, dies between the discount factor plus the probability that the person continues alive and divide it by 1 plus the interest rate and multiply it by the present value of the insurance of the year k plus 1. The last way to do it will be the scotcholate.
So, premium of a life insurance. Do you represent the premium of a life insurance policy for a person at age X? So this insurance only pays if the death occurs to the end of the year during the term end of the police exist. So we can see the premium, the formula to the premium to these payments, and we consider the probability of life and hx and the probability of death in the hx plus k. Then in k is the number of years this person lives, and we consider the present value of this payment during the period of time of this life. So now we see how we program it in Excel. This function will be to calculate the present value of a monetary unit payable at the end of the year of the death of the person with hx. The parameters that this function receives are the variable int x as integer, the variable int n as integer, and the variable bdl tags as double. So all we are going to include this set of variables in the function, and we are going to declare this function as a double. The variable dvlv is the present value of the payment and the variable key to account. So we will start of ax1n function value at 0 and declaring the value of dvlv, the present value of the payment. It's 1 divide, so 1 plus dvl tax. dvl tax is the rate of this exercise, and declaring the value of dvlv. So we will use a for with the variable key equal to 0, and to end the variable to int n minus 1, and the for will continue cut times to the end the exercise. Variance C. Variance of the random variable C. The random variable C represents the present value of the benefits given by the insurance policy. So we can see the formula for this problem, variance of C.
So having these two formulas, we just apply them here. So we can have the insurance and the variance, and then we obtain the premium. This just by summing up the insurance to the k value, which is sigma, times the square root of the variance. This square root of the variance means the standard deviation. So having this, to calculate the probability of ruin, we just need to simulate losses with the inverse normal distribution function with a randomized probability, a set mean, and a set standard deviation over here. So here in this part, we have that a 0.38 loss. That is a loss. So we mark the ruin as 1. But like in this random loss, we have a loss, an expected loss of -1. And that's not a loss, that's a gain. So we mark the gains with zeros and the losses with ones. We do that with all these simulations. And using the central limit theorem, we just get the average of all these numbers over here. So we can have a probability of ruin of 4.6 or of 4%. And we can see that this probability tends to 5%. Now we can go to capture our first insurance portfolio for 60 people.
We need to grade the number of simulations we want, where we then take the inverse number of each simulations, and we need more things like the result of the AX1N, the variance, the premium one, the premium two, and the difference. And then now we grade the number of simulations, and we need the simulation loss and the sum of the premiums. And for to know, or if we want to know if we have a loss or profit, we need this formula. So if the simulations loss is less to a sum of premium, we have a profit. And if we have a profit, we have in this row a 0, or if we have a loss, we have a 1, like this example.
If we look at this approach, we're using an approximation. And the central limit theorem states that for this approximation, we need enough random variables. And in this case, we're using 60, but we're not sure if that is enough. So we need to look at a different approach. For this approach, we're using this function, which calculates the probability of ruin. First, we need to look at this variable name in pop. For this one, it's necessary to use U-bound. This function tells us the largest subscript of the array ages. Basically, this counts how many ages we have in the array. If we have a 60 people portfolio, then in pop will be equal to 60. Now, PNU stands for prima neta única, and we will be accumulating in this variable. So we need to start with an initial value of 0, and we will be accumulating with this loop over here. So this loop goes from 1 to in pop because we want the premium, the sum of the premiums of all the people in the portfolio. And for each one of them, we will be starting with int x. Int x indicates the age of the person in the position k of the array ages. Then we're going to generate a distribution table with the probability that the person with this age dies in the next k years. We generate a table that looks something like this with all these probabilities. Now, in this exercise, we are calculating a premium that is the actuarial present value plus k times the sigma. So we need to calculate this one over here and this one. The actuarial present value will be calculated by this function. Then the standard deviation will be the square of the second moment minus the first moment to the power of 2. And then will we sum what we're having plus the next premium and so on. Now, for this variable, we're using this function over here, which is the same as this one. No simu is basically the number of simulations that we want. And this loop over here is calculating the financial present value of one monetary unit with this formula 1 over 1 plus the interest rate to the power of 1 plus this function over here, which is basically an integer random number that will be generated by this function. And this random number will be taken by a distribution table. So if we look at our table, these are the numbers that we are going to generate, which is the years that a person has to live. And all those present values will be accumulated in this array. So if we go back to this one, for every single person in the portfolio, we will be generating a number of simulations because we want to have something like this for the first person, all the simulations, for the second, all the simulations. And we're doing this because the next thing we were going to do is going to be sum all this column, and we're going to compare every single one of them with the premium that we are charging.
Okay, so going to the final step of this procedure and to finish explaining the program in macros for this simulation, in order to calculate if there's a ruin or not for every person in the insurance portfolio, first we clean our variable MC and use a for cycle to take into account each vector simulated on the pass function, which was this one that was explained by my friend Alfredo. So we accumulate every vector that we created here, which was VP pop, and sum them all up in here to later compare them to the premium paid. So the premium paid, here's the comparison of the sum to the premium paid. And as we explained earlier, a 1 means that to this specific sum, there's a ruin, and a 0 means that there is no ruin at all. So, as we can see here, if the sum or this variable called summa is higher than the premium paid, we have a loss. So we have a ruin. But if it is lower, we have a gain. So we don't have ruin. Finally, finishing the cycle, we calculate the average, which we need to obtain the variance in this next for cycle. So here we calculate the mean or the average, and then we calculate the variance over here. And that will for last be used to gather the two ends of the parabola that represents our confidence interval with 95% of probability, which you can remember, we have a parabola and we need these two ends over here. That's why we're using these two formulas over here.
To remember a little bit about our second spreadsheet, I'll reframe the table of our insurance portfolio in detail.
Okay. So having all this programming all gathered up, we created a random portfolio that consisted in 60 different people with different and randomized ages. So here we have 60 different people with randomized ages between 15 and 99. So we used our same rate, 3%, and or K that was explained before as 0.216. Okay, so having the simulated ages, we use our function of the temporary insurance AX1N and call here and call the age of the person. So we call the age of the person, which is 18 in this specific example. Then we call omega minus the age, which omega is 100, that is like our limit age, minus the random age, and then finally the constant rate, which is 3%. Okay, so for the variance, we call the same function, but just as in the first spreadsheet of the Excel, we call a square rate and subtract the insurance to the exponent 2. This represents the variance equals EX to the 2 minus E to the 2X formula over here, as we can see. Okay, so for the premium, same procedure here as in the first sheet where we calculated the premium for a 40-year-old person, but now for each person. Okay, we just need to sum the insurance plus the sigma times the standard deviation and times 1000, that is the benefit. Okay, and now let's focus on our probability of ruin. As you can see here, we simulated random losses using the Excel function of the inverse normal distribution, given a random probability, a calculated mean, and a standard deviation, given all these randomized ages. So then we summed all the premiums that we calculated over here, and we see if the random loss is actually a loss or rather a gain. This we do by comparing these two values over here. So if this value is higher than this one, we have a 1. But if this value is lower than this one, as in this case, we have a 0. So we have no ruin. And using the Central Limit Theorem, we get a probability of ruin that tends to 5%, a little bit higher than 5%. So at first, our Monte Carlo program that we already explained in the past minutes with confidence interval of 95% diverged a lot to this number over here obtained by the Central Limit Theorem. What we did here is we augmented the number of simulations. So we have a lot of simulations, but also our constant K was augmented from 0.216 to 0.218. Sorry, for 0.28. This is how we ended up with a more similar probability over here. And that also tends to 5%. Okay. So just to end this explanation, we can observe that the premium 2, which was calculated with the higher K times the standard deviation, creates a difference between these two premiums. So this one was calculated with this 0.28 sigma, and we have higher numbers of premium in all these people. With a higher sigma, we have higher portfolio. So then we just calculate the difference between these two, and we can see that if we keep creating random simulations, so we keep creating random simulations, and we just need to look at this number over here. The maximum of variations tends to 3%. And looking at the ages of this higher rates or higher variations, we can see that the people with 20 years, 26 years, 38 years, 49 years are the people with higher variations. That means there are the people that pay more for premium for this insurance.